Dear colleagues, welcome to the audio slide presentation of the article titled "A Novel Laboratory Blanking Apparatus for the Experimental Identification of Blanking Parameters." The research was published in the Journal of Materials Processing Technology. My name is Špila Balka, and in the next few minutes I will discuss the construction and abilities of the newly designed laboratory blanking apparatus. The most important part of the blanking apparatus is the cutting module. It consists of a detachable housing and cutting elements. The movement of the punch is enabled by a piston, which is accessible from the outside at the back of the body. The die lies in the die holder. Alignment of the die can be adjusted by the micro-adjustment screws. The specimen is inserted vertically in the cutting module and is held in position by 8 strong magnets. Punch has a 1 mm tip extension in the center used for displacement measurement by displacement laser. The force is measured by a force transducer behind the punch, and the punch acceleration is measured by the punch accelerometer at the base of the punch plate. The novel laboratory blanking apparatus offers quasi-static and dynamic experiments. The configuration for quasi-static experiments consists of a support block on which the cutting module and the fixation block are attached. Movement of the punch is achieved by turning a fine threaded screw in the fixation block. The speed of the experiment depends on the torque applied to the screw. The weight of this configuration is about 500 kilograms. For dynamic experiments, the apparatus is raised for an arbitrary angle and the fixation block is replaced by an impactor. In this configuration, the blanking apparatus has about 800 kilograms. For a dynamic experiment, the impactor is released from rest at an arbitrary position on the support. Its initial potential energy is transformed to the kinetic energy at the time of the impact with the piston. Various blanking speeds can be achieved, the lowest depending on the circumference of the punch and sheet metal characteristics. Initial placement of the impactor can be determined up to 1 mm accurately, resulting in determining of punch displacement up to 10 micrometers accurately. 3 basic types of measurements can be performed: full experiments, partial experiments up to a certain punch depth, and sequential experiments where the full punch penetration is achieved in consecutive partial steps. For this research, a circular punch die set was used with punch diameter of 10 mm and clearance of 25 micrometers per radius. Specimens were prepared from low-alloyed steel sheet of nominal thickness of 0.5 mm. As mentioned previously, the apparatus offers precise alignment of die according to the punch. Visual verification of the clearance is possible. The photograph on the left showing centric punch and die alignment, and the photograph on the right showing an eccentric punch and die alignment. Dynamic experiments showed that acceleration of the punch during blanking can reach up to 600 Gs at the blanking speed of 450 mm per second, whereas accelerations did not exceed 3 Gs at quasi-static trials. As the force transducer is placed behind the punch accelerations result in relatively high inertial forces measured by the transducer. Thus, inertial correction was performed. In addition, sheet metal surface temperature was measured by the use of a high-speed thermal camera. Blanking with speed of 200 mm per second resulted in raising of sheet metal surface temperature locally for about 20 degrees Celsius. Measurement of sheet metal surface velocity during blanking with velocity lasers showed that, while blanking with 200 mm per second, the slug as well as the scrap respond dynamically. In conclusion, the presented novel laboratory blanking apparatus enables a wide range of detailed experiments with great control over the parameters. New insight in the process has been proposed by introduction of the inertial correction and new approaches to measurement of punch die misalignment, sheet metal surface temperature, and sheet metal surface velocity. Additionally, partial and sequential experiments provide basis for material characterization in terms of plastification and damage.